How does the query execution engine work? How does it process the inputs and produce the outputs? In what order do the different operations get executed? Do they run in sequence or in parallel? If you want to know the answers to these questions, let's jump in. Hello and welcome. My name is Elhelw. Today I'm going to be talking about the last step in the query engine, and that is the query execution engine. In previous videos, we talked about the life cycle of a SQL query from the point it gets submitted to the query engine, passing through the different components, starting with the parser, which parses the tree and produces a list of tokens and then builds the parse tree. This then goes through the analyzer, which processes this parse tree and then converts it into the initial query plan. The initial query plan is then fed into the query optimizer, which uses the statistics and the catalog information to enumerate all the different possible plans, estimate the cost of each, and then choose the final execution plan. And then that final execution plan is the input for the execution engine, which we are going to talk about today. I will post links to the previous videos that talked about some of these components, including the query optimizer, as well as the overall video that I mentioned in the beginning. So all the links will be in the description as well as up on the screen. So feel free to review these videos before continuing with the execution engine video. So like I said, the execution engine is the final step which produces the results. The execution engine operates on the execution plan that is given by the query optimizer. The execution engine is responsible for running all the operations in that execution plan and using them to produce the outputs of the query. That execution plan, if we remember, we've seen many of these plans before, but just as a reminder, the execution plan is organized as a tree of different operations, right? Let's see an example of one such tree. So here we have this query that selects from two tables joined on some condition, and then we have a selection predicate on table b.amount is greater than 100, and then we have a limit 5. So this is what the execution plan might look like. So we have the operations organized in a tree. One thing to remember as well that we mentioned before is that this execution plan is a physical plan. So all these operations are physical operations, which means that they have actual implementation. So for example, we have hash join, we have table scan, and so on. You might have other things like index scan or nested loop join. You might have sort-based aggregation or hash-based aggregation. So these are actual algorithms that we have discussed also in other videos. And then the execution engine should be able to start running these implementations. You can think of it as different functions, as if like we have a function that does the hash join functionality, another function that has the scan code, another function that has the code for the selection, and so on. So all these functions together, as well as the framework that invokes them, this is what the execution engine is. One thing to note about the tree or the execution plan is that each plan might be different depending on the original query, right? Like, in one query, you might get a hash join that has two scan nodes directly beneath it. In another query, you might get like a hash join with a selection, and then the selection has, a sort or something. So these nodes in the tree might be different for each query. So you don't know, for example, the hash join, what the inputs of the hash join will look like. Or like, are they scan nodes? Are they selection nodes? Are they aggregation nodes? You don't know. So the hash join, for example, I'm just using it as an example, but the same applies for any other node. It needs to be able to call its children nodes, regardless of what they are. For that reason, all of the different nodes, all of the different operations need to have a common API. So there should be like a common way of calling all of them without knowing what they are. In object-oriented terminology, for those who are familiar with object-oriented programming, you might think of all of these as having the same interface or inheriting from the same superclass. So if we imagine that we have a superclass called node, then all of the operations should inherit from that superclass and have the same functions or same public methods that you can call. In this way, the hash join, for example, or whatever node we're dealing with, can then call its child regardless of what type of node it is, because it knows that it implements that functionality. So it doesn't need to know what the children are. And this is a very important thing in the query execution because these operations are composable and can be in different order for different queries. Now, with that in mind, the implementation of these functions will be different, right? So like the implementation or the body of the table scan node is different from that for the hash join or for the selection and so on. So even though they may have or they should have the same API, the same function signature, of course the implementation of these functions will be different. The way these will be implemented depends on what we call processing model. So we have different processing models. These are different ways in which the execution engine might work. And depending on which of these models we choose, the implementation of each of these operations will be done in a different way. So we're going to talk about 3 different processing models, see how they affect the implementation, see how they work, and then discuss also the advantages and disadvantages of each. So with that, let's start with the first one, and that is a model that we call the materialization model. The materialization model is basically, you can think of that as the default way that you might think, or the simplest way you might think about these operations, right? When you think about scan, okay, the scan node just outputs all the rows from a table, right? That's what it does. The selection node, it takes whatever the inputs of that node, applies a certain condition, and returns only the ones that satisfy the condition. Like this is what the select operation is, right? Like in terms of relational algebra operations when we used to talk about those. When you talk about like a hash join, for example, hash join takes all of its, let's say, right side inputs, uses those to build the hash table, and then takes all of the left side inputs, looks them up in the hash table, and produces the join results. So the way I'm thinking about this is basically the way the materialization model works. Each operation processes all of its inputs and produces its entire output. All of it happens at once. So again, like if we talk about the scan operation just produces all the rows from a table. Once it does that, you never need to think about the scan again. Hash join takes its left side, all of it, builds the hash table, takes its right side, looks them up in the hash table, produces all the output, and then it's done. So for that to happen, each node has a function, let's call it getResults, which returns all the results from that operation. So as we said, like all of the nodes need to have the same API. So in this case, the API is this function, getResults. Each operation needs to support that function. And of course, for a node to produce its own outputs, it needs to get the data. If it has children, it needs to call the getResults from its child nodes. So if we were talking about selection, for example, select node, the select node, in order to produce all its results, it needs to call the getResults of its child. So get all that data, all these rows, apply the condition, and then it should return the rows that satisfy the condition as the return of the getResults function. Let's look at some of the implementations of getResults for different operations and kind of like see what they look like. So in the query that we've seen, for example, we have some operations like table scan, select, hash join, and limit. Of course, there are many other operations that are not in this plan, like we could see nested loop join, we could see aggregation, and so on. But let's just look at the implementation of the operations that we have here. So starting with the simplest one, the table scan. Again, so we have a class table scan, which inherits from the node superclass, and it has this getResults function, which returns a result set. So it returns, a set of results. So for this function, it's pretty simple. It just, iterates over the rows in the table, puts them in that result set, and then returns that result set. So once you call, table scan getResults, it will return all the rows from the table. Let's look at the next one. That's the select node. So the select node is not a leaf node, so it has a child. So that's why we have a child here. Again, it has the getResults function. For the getResults to return its outputs, it needs to call getResults on the child first. So regardless of that child, what it may be, like the child could be a scan, it could be another select, it could be a join, it could be whatever it is. But because we know that they all implement the same function, you can just call the getResults and you don't care about what the child is. So it will call getResults on the child, and then for all the data that is returned, in each row in that data, it will apply the filter or the condition, and for the ones that satisfy will be added to the output and then returned. So this is the simple algorithm behind the select operation. Let's look at the hash join. For example, hash join is a little more complicated. So hash join is a binary node, so it has two children. It has a left and a right child, as we have seen here. If you remember when we talked about hash join has, you can think of it as two steps, right? Like first step is building the hash table. Second step is looking up, rows into that hash table. So we're going to use the left side to build the hash table. So in this case, it will call, get results on the left child. Again, it doesn't care what that left child is, as long as it's something that supports get results. So the results that get returned from that, it will iterate on that and use those to, add them to the hash table. Once it's done with that step, it will go to the right side, call get results on that. Again, doesn't care what it is. These results, it will start looking them up in the hash table. For every row that is found, it will, produce a joined row between the left and the right and add that to the output buffer, and then that is returned as the result of the join. Let's also look at the limit node. So the limit operation basically says, okay, I want to return up to n rows. In this case, for example, limit 5 means that we can only return maximum of 5 rows. So what this does is basically, again, this is a node that has a single child. So it needs to call get results on that child and then return the first n rows out of that. So this is basically the simple implementation of what these operations might look like using the materialization model. Now, how does that work actually like during execution, right? So let's look again at the plan. In order to return the results, like remember, query execution, that's the last step in the query engine, right? So this actually is what is going to return the results. So to return the results from this plan, you basically call get results on the root node. Again, we don't care what the root node is. We're just going to say root.getResults, and that will start executing the query. So in our case, the root is a limit node. So this basically means that we need to execute the get results function for the limit operation. So to do that, we need first to get results from its child. So this is part of that code. So this will call get results on the hash join node. So the first step for that is calling get results on the left child. So this left child happens to be a table scan. Table scan, what it does is basically it's just going to return all the rows in that table. So that will return that to the hash join code. The hash join code will take all these rows, start building the hash table from them. Once it's done, then it's going to start calling get results on the right side. So that means for the select operation, this also needs to start calling get results on its own child, which is the table scan. This returns a bunch of rows to the select. Select will start applying the condition on each of these. The ones that satisfy the condition are going to be returned. So this is going to go back to the hash join. The hash join will start iterating on those, looking them up in the hash table. Whatever data matches is going to produce join rows and return those to the caller. The caller is the limit. It's going to return the first 5 rows out of that, and that will be the output of the query. One thing to note here is that each operation, we call it just once. Like each operation executes from start to end. Sure, if it has to call some other stuff, it does that. But once it has control and once it has all its inputs, it runs its algorithm, produces all its outputs, and then it's done. We never go back to that. For the final results to be returned, like the results of the limit at the very top, it needs to wait until all the other nodes have finished. So we will not see any results as someone who is looking from outside all of that. Will not receive any results of the query until every single node in that query has finished producing its own outputs, right? So this is just something to take into account, and we'll talk more about that a bit later. These outputs of every node, right? So the table scan is producing a bunch of rows, select is producing a bunch of rows. So we call these intermediate results because they are intermediate results between, two different operations, as opposed to the final results, which are returned to the caller or to the application and whatnot. So the intermediate results are usually passed in memory, right? Assuming that they can fit in memory. If they cannot fit in memory, like you have too many rows, for example, then in some cases we may have to spill them to disk, which of course means more I/O, which means the query can get slower if we have too many rows. All right, so let's talk about the pros and cons of this model, right? The materialization model. So first of all, the advantages. First advantage is it's very simple to implement, right? When we were talking in the beginning about the implementation of the different operations, this is basically how you think about them. This is how you think about the scan. This is how you think about the selection. Just you return all the rows, or like apply some filter on the rows and return the ones that satisfy it, and so on. So very simple implementation, very intuitive. It doesn't require any coordination between the operations. Each operation assumes that it will get all its inputs, it will apply the algorithm and return all its outputs, and that's it. Each operation is called only once. This means that there is very little overhead from function calls. Each of the functions in the previous plan, in the example, has been called only once. So that is a big advantage in that case. The materialization model is very good for OLTP queries. OLTP queries means small, operational queries that are usually very simple, either point queries or operating on a very small number of rows, and they usually don't have too many operations as well. The reason it's good for these queries is because, like I said, it has few operations. So remember when we said that you cannot produce output until all the nodes have produced their intermediate results. So when you have few operations, it means that you don't have to wait for too long. And also because usually the intermediate results are also small, because again, it's a simple query operating on a small number of rows. So most of the time, these intermediate results can actually fit in memory and you don't need to spill to disk. So the queries can be relatively fast. Now, the disadvantages are, well, one is the opposite of what we were just talking about. It's not good for OLAP or analytical queries, because these queries are usually very complex, have many operations. So it means that you have to wait for all these operations, all these nodes to produce their outputs before you start producing the final outputs of the query. So this means the query will take a long time. And also because these queries usually operate on huge amounts of data, so the intermediate results are going to be very big, which means very likely they will not be able to fit in memory. So each operation will likely spill to disk, so that's a lot of I/O. So the queries end up being extremely slow if you use the materialization model for such queries. Another thing is that there might be actually some wasted work or unnecessary work that's being done as part of processing the query. And a very easy example to demonstrate that is the limit operation, right? Like the example that we've seen has a limit at the top. So in this particular case, let's assume some numbers. Let's say the table scan returns 1,000 rows, and the other table returns 10,000 rows. The selection, let's say, it obviously will filter out some rows, so let's say it returns just 2,000. Now the join of these rows, let's just assume for the sake of this example that it will produce 50,000 rows as the result of the join. The limit is going to return 5 rows. So we've done all this processing, we've returned all these rows from below, even though we did not really need them. This could not be avoided because the way this works is that each operation just needs to return all its outputs before the next operation can start. Did we need to scan all the rows from table A? Yes, because we need to build a hash table. But did we need to scan all the rows from table B? Probably not. But how many did we need to scan? You don't know, because you don't know how many are going to pass the selection or how many are going to join. So this is why you need to scan all of them, and then at the very end just pick the first 5. So this is a lot of wasted work that makes the query unnecessarily slow. So this is something that's important and we need to know about the materialization model. Now we go to the next processing model, and that's called the Iterator model. The Iterator model addresses some of the issues that we've just seen in the materialization model. Now, for the materialization model, as we said, each node or each operation has this get results function which returns all the outputs of that operation, right? The Iterator model does not return all the outputs. The Iterator model returns one output at a time. So instead of a get results function, it has a get next function. Get next, when you call that on an operation, it will return just the next row. So to get all the outputs, you need to call that function several times. Each time it's going to return you the next row until at some point, if it runs out of data, or like if the operation says that there's no more data to return, it's going to return like a special marker end of file indicating that there is no more data to return, so the caller will know that it's done. So as I said, each call for get next returns just the next row. So this means that the operators or the nodes are active for a longer time. In the materialization model, you call the get results, it's going to return everything, and then that node is done. You don't need to do anything again with it, right? But here, you call get next, it's going to return one row, but it needs to stay active because you're going to call get next again to get the next row. And part of being active, it needs to know like where it is right now or where the next row is. So it needs to maintain some state information, right? So it needs to say, okay, like this is what we've returned so far, and the next time I'm going to return this data. So it needs to maintain that state somehow and know how much it has returned, or like, you know, what the next row is. Besides the get next function, there are a couple of other important functions that these operations need to support. There's usually like an open and close function, kind of like think of it as the constructor and destructor of the object. Because we have a state, right? Then we need to initialize that state somehow. So this usually happens in the open function. Also, any setup work or any preliminary work that needs to happen before we start returning rows usually takes part in that open function. And then you have the close function, which does any cleanup or releasing resources and stuff like that. But as you can imagine, most of the work happens in the getNext function. All right, so again, let's look at some example implementations in the iterator model. The table scan object or class, now it has the getNext function instead of the getResults. So now in the iterator model, we don't have a getResults function anymore. All the operations need to support this getNext function. An example of the open function as well is it needs to initialize a cursor. A cursor is, you can think of it as a marker or a pointer on the table that says this is the next row that we're going to read. So each time you call getNext, it will read the row at that position and then, you know, advance the cursor to the next row so that you know the next time which row you're going to read. And this is basically what the getNext function is doing. It's going to read the row at the cursor location. Of course, if you have reached the end of the table, then you need to indicate that this is done and you need to return end of file. Otherwise, you're going to, you know, return the row that you've read and also advance the cursor to be ready for the next time. If we look at the select node, remember it needs to, you know, apply condition and return the rows that satisfy the condition. Except this time we're not going to return all the rows at once. We just need to return the next row that satisfies the condition. So in order to do that, it will call the getNext on its child, and of course it needs to also, you know, take into account if that returns end of file, then this means that the child is done, so it will just return end of file. But if it gets a row from the child, it will apply the condition. If the condition is satisfied, it will return that row. If it's not satisfied, it will get the next row from the child, and so on. So it will keep getting rows from the child and applying the condition until it finds a row where the condition is satisfied. Because getNext, it needs to return a row, or end of file will only be returned if we reach the end of the data. So it cannot return end of file just because the row did not match the condition. It may have to call getNext on its child multiple times until it finds a row that satisfies the condition, and it will return that row. The limit function, as we have seen before, limit function needs to return up to, you know, a certain number of rows. So it will maintain the number of rows that it has. Each time it returns a row, again, it will call getNext on the child and return the row, and each time it will decrement that counter until it reaches 0. Once it reaches 0, it means that it's done. It will return end of file, even if the input still has more rows. In that case, it's not even going to call getNext anymore on the child. Once it has reached the number of rows that it's supposed to return, it will just return end of file. And then we have the hash join. Again, hash join, getNext is supposed to return just one row, right? But to return one row, especially the first time this is called, there needs to be some setup happening here. It needs to build the hash table. So to build the hash table, it's going to call getNext on the left child over and over and over and over again until there is no more rows coming from the left child, basically until the left child returns end of file. And then it will start calling the right child. This only happens on the first call. So on the first call, because as you can see, you have a state variable here that says hash table ready. So this starts with false. If that's false, then it's going to start building that hash table. But once that is done, then it's going to set that variable to true. So it means that the next time you call getNext on it, it's not going to do that work again. It's just going to fetch the next row from the right child, look it up in the hash table. If it finds it, then it's going to return the joined row to the caller. This is an example of something that is slightly more complicated. Okay, let's look at the execution sequence. So again, this is the plan that we have. In order to get the first row or the next row, you're going to have to call getNext on the root. Compared to the last time we called root.getResults, and it was just a single call that returns all the outputs, right? Here you're going to have to call getNext multiple times. So each time you call root.getNext, you expect that to return the next row of the output, until at some point it's going to return end of file, which means that the query is finished. So what happens when you call getNext on the root? So the root is a limit node. So this is the code that we have. It will start by calling getNext on its child, similar to what we have seen before in the materialization model, right? So the child is a hash join, needs to call getNext on its left side. This is a table scan. When we call getNext on the table scan, so it will set up the cursor and all that, and then we'll start returning the row at the cursor position. So that row will go up to the hash join node. It will add that to the hash table. It will call getNext again, so it will repeatedly do that. So return the next row. It will call getNext again, so on and so forth, until at some point the scan node will say that it has reached the end of the table. So it's going to return end of file to the hash join node. So once it returns end of file, the hash join node knows that, okay, I'm done building the hash table. Now it's time to start calling the right child, because now I'm going to start looking up into that hash table. So calling the right child here is the selection node. Again, it needs to get next from its child, which is the scan node. So the scan node is going to return first row, again, with move the cursor and all that. The select node takes that row, applies the condition. Let's say in this particular case, the condition that, this row did not satisfy the condition, so it's going to call getNext again on the child. The scan node is going to return the next row. Let's say this row satisfies the condition, so the scan node is going to return that up to the hash join node, which will look it up in the hash table, and let's say it matches, so then it will return a join output to the limit node. Limit node will see that it is still has not exceeded the limit, so it will return that row up to the caller. So all this work that we have done, we did just the necessary work to return a single row out of that query. We did not scan all of table B. We had to scan all of table A because that is necessary to build the hash table, but we only scanned 2 rows from table B so far. We did the join just on one output and so on to return that one row. So to get the next row, we're going to have to repeat that process again. So we're going to have to call getNext on the root again and go through a similar process, except this time we're not going to build the hash table because hash table ready is going to be true, so we're not going to do that part. We're going to directly start getting rows from the right child and trying to match them with whatever we have in the hash table. Also, the next time when we get to the table scan B, it's not going to start from the beginning of the cursor, because the cursor knows where we are, so it's just going to get whatever row is next in that cursor. Note that for the limit, right, once we've done this 5 times, the next time we call it, it will realize that we have reached the limit and it will stop the execution because it will return end of file. So we will not need to scan everything from table B. So this is in comparison to what we did in the materialization model. Here we only do the necessary work to return the result that we have in the query. Once we've returned, in this case, 5 rows, we're not going to read the rest of table B or do the rest of the join or any of the other operations. Okay, so what are the pros and cons? The advantages, first thing is that it allows for pipelining. Pipelining means that you have multiple active operations at the same time, and you start seeing outputs even before you're done, reading all the inputs. It's kind of like, when you look at a pipeline in a factory, right? You have multiple parts of that production pipeline happening. Like the first stage of the pipeline might still be getting some inputs, but at the same time, there is output being produced at the end. So this means that you start seeing results much faster than the materialization model. The materialization model has to wait for everything to finish before you start seeing the results. Here, this is not necessary. It also avoids unnecessary data read. As we explained in the case of the limit, it only does as much as needed to produce the outputs that we are looking for. And once this is produced, the query is stopped. It also does not require keeping intermediate results in memory, which we had to do for the materialization model, remember? Because each operation in that model needed to produce all its outputs, keep it in memory, or spill it to disk if needed, and then the next part would have to read all that, do all its work, and then produce its output and so on. In this case, we're producing just one row at a time, so we don't have to maintain all that data in memory. Of course, there are some cases where we might also have to spill to disk and so on, but that doesn't happen as often as in the materialization model. The Iterator model is supported by most, if not all, database systems. This is like the most popular processing model. So most database systems that you have seen or that you've dealt with are most likely using the Iterator model. The disadvantages are, first of all, the implementation of each node or each operation is slightly more complex, because now it has to take into account how does it deal with end of file, how does it return just one row, so it might need to loop on the child and so on, like as we've seen in the selection, for example. So the implementation may not be as intuitive as it was in the materialization model, so that's one disadvantage. Another thing that we have seen is also there's a lot of context switching, right? We're calling these functions back and forth. Each function call means that we have to put stuff on the call stack, take stuff from the call stack, and so on. That introduces a lot of overhead, which can also be expensive, because each function is called so many times until it ends up returning all the rows. It's not just one call as we used to do in the materialization model. In some cases, some operations can also be blocking. Blocking means that it's something that cannot produce outputs until it has consumed all its inputs. An example for that is hash join, for example. It has to consume all its left side to build the hash table, so it will not start producing outputs right away until it has consumed all the left side, and then it starts looking at the right side. Sorting is also a blocking operation. It cannot produce any outputs until it has read all its inputs, sorted them, and then start producing them in sorted order. Aggregation is the same thing. So there are some operations like that, and if you have operations like that in the query, then you end up also having to wait until these operations have read everything before you start seeing any outputs. So now that we've talked about the materialization and the iterator models, the third model is going to be the vectorization model. To talk about the vectorization model, let's take a step back and compare the two models that we've talked about so far. So we have the iterator model and we have the materialization model. Each call to a function or to an operation, how many rows does it return? For the iterator model, each call returns just one row, as we've seen. On the other end of the spectrum, the materialization model, when you call the get results function, it returns all the rows, all the outputs. These are the two ends of the spectrum. The vectorization model, which we're going to talk about now, is somewhere in between. So it returns n rows for n greater than 1. This vectorization model can also be referred to as batch processing or block processing, because it returns a batch of rows each time. So not a single row like the iterator model, and not everything like the materialization model. It's tries to get the best of both worlds. So the API now is a little bit different. It's called getNextBatch. Of course, just to clarify, you might see different names in different implementations or in different databases. All these functions may be called something different, but you get the gist of what it means. So getNextBatch, each call returns the next batch of rows or next group of rows. Until, of course, it reaches the end, then it will return end of file like we've seen before. The good thing about that is that you can usually control the batch size, so the number of rows in the batch, and that can depend on the memory that you have. So you can set the batch size to a number of rows that can fit in memory to avoid having to spill to disk. So in this case, it avoids the problem with materialization where you have to pass all these huge intermediate results. So now the intermediate result size is smaller because it's controlled by that batch size. I'm not going to list all the implementations of all the operations again, but just for reference, let's compare one operation between the three models. Let's take the table scan operation, for example. So in the materialization model, that was the implementation that we've seen. Just iterate over the table, and return all the rows. In the iterator model, it had to use that cursor, get the next row at the cursor, also take into account if it's an end of file or not, and advance the cursor. Now for the vectorization model, it's even more complex than that, because aside from having to look for the end of file, you also have to keep track of the batch size and whether you've reached that batch size or not. So this is what the code for the table scan will look like in the vectorization model. It either returns a batch or a result set that has that size of or number of rows, or once it reaches the end of the table, that returns the end of file marker. What are the advantages of this model? As I said, this tries to get the best of both worlds. So first thing is that it does not need to produce all the outputs of each operation before you can start seeing outputs of the query. This means that it will start producing results before it has finished reading all the data, right? So in this case, it's better than the materialization model in that sense. Each operation produces a batch, which can usually fit in memory. Again, you control that by controlling the batch size. So again, this avoids these huge intermediate results that we used to deal with in the materialization model. So those are smaller, which means that usually they can fit in memory. It can work with large data sets. Remember, the materialization model had a problem with large data sets because the intermediate results would have been too big. Now, controlling that batch size enables us to work with large data sets. You'll just have to have more batches, that's all. And it can also work on complex queries, even if you have too many operations, because again, you don't have to wait until all of them finish before you start seeing results. The query will start producing results much faster than the materialization model. Granted, slower than the iterator model, because you still have to produce batches rather than single rows, so it will take longer to produce these batches, but it's better than the materialization model in that case. One thing that it's better than the iterator model at is that it has much fewer function calls, right? In the iterator model, you have to call the function for every row. Here, you have to call a function to produce, let's say, 100 rows, like one batch. So the number of times you have to call functions is much less. This means that you have, much less overhead than the iterator model. Now, the disadvantages are, first thing, as we have seen, the implementation is much more complex. You have to take take into account the end of file, the batch size, and many more things. This adds complexity to the implementation. Also, compared to the iterator model, it takes longer to start producing the first output, because again, you're not just doing work to produce one row, you're doing work to produce a batch of rows, so naturally that will take longer. It may also have some wasted work in case of things like limit and so on, but it's not as bad as it was in the materialization model, right? Because again, you're not producing everything, you're producing one batch at a time. So in one of those batches, you might realize that you've already produced more than you need. But the good thing is that once that batch is done, you're not going to produce more. So it's slightly, you might have some waste, but it's not usually that big. Okay, so these were the three models that we've talked about. Aside from that, there's also another important concept in query execution, which is pull-based versus push-based processing. Let's see what that means. So everything that we've talked about so far was something that is called pull-based. Pull-based processing means that each node is pulling its inputs, from its children. The children are not active or are not doing anything unless their parent is pulling from them. So like each node is asking its child, hey, give me the next row, or give me the next batch, or give me all the rows. So as we've seen, like the execution is top down, like it's driven from the top. The node at the top calls its child to give it the next output. That child starts calling it its own child. So each node is pulling row, and when it needs another row, it will call the child again. The child is not going to do anything on its own until the parent calls it. So that's why we call it a pull-based processing, and it's top-down. And like I said, each node is pulling data from its children. So if we look at quick animation to illustrate that, again, we're starting from the top. You call, let's say get next or something on the top node. This will call get next on the child. The node that has the red arrow is the node that is currently running, whatever code is currently running. Anything on top of that is usually waiting for, for that to return. Anything below that is just not doing anything. So hash join, for example, when we are executing the hash join, the limit is waiting for the hash join to return. So it's like just waiting. And the others below it haven't even started. The hash join is going to call the table scan. So now execution is at the table scan. This will return a row to hash join. It might call it again to get the next row, and again to get the next row, and so on, until it's done with that side. Then it's going to start calling the other side. And again, like the execution is moving from one to the other. Each of these nodes is only active when it's being called by its parent, right? So the select node, for example, has not done anything so far until the hash join started calling it. So the select node is going to call the table scan. This will return a row, which will return something back to the hash join. And now these nodes at the bottom are, again, like they're not active until they get called again next time. And so on until we return, let's say, a row. So like we've seen in this animation, while one node is executing, whatever node that had the red arrow pointing at it, everything else is waiting. You can think of this as like single-threaded execution. So everything else is waiting until this node is either is done and returns to the parent or starts calling the child again. The advantage of this model is that it's very simple to implement and it's also very easy to debug, right? You can easily know at any point in time where the execution is, which node is executing. It's just as simple as tracing into some function calls and then returning from those function calls and so on. So there's nothing complicated about it. It's just regular function call tracing. The disadvantage of that is that it does not have any parallel processing. At any point in time, just one node is active and doing some work while the others are idle. So this is the trade-off here between the simplicity and the performance. Now, the other side is what we call push-based processing. So clearly we're trying to increase parallelism now. So how do we do that? Push-based processing, just judging by the name, instead of each node pulling data from its child, we're going to try to make the children push data to their parents. So this is going to be bottom up. So it's going to be driven from the bottom, and nodes are just going to push their inputs upwards. In order to be able to do that, we need to add some buffers between the nodes. So adding those buffers mean that each node can independently start working, whenever it produces data, they can just put them into these buffers. And then the nodes above, once they see that the buffers are ready or have some data in them, they can start also pulling from those buffers and producing more data, putting them in the buffers above them, and so on. So this way, the dependency between the nodes is broken. Like we don't need to have these direct calls into the child. Each node just puts things into the buffer independently of the others, and the others also just work on these buffers. So let's say how this works. Let's see how this works. Once I run this query, all the nodes will be activated at the same time. So not just the top node, but all the nodes will be activated. Hey, like saying all of these can work. You can have them working in concurrent threads and whatnot. Now the ones that are ready, the ones that have ready input, are only the ones that are going to actually start. Anything that is waiting for input is going to be idle for now. So the ones that are ready for now are the table scan nodes, because they don't have any children. They can just start scanning the tables. So they're going to start scanning and putting the rows in that buffer. Once they start putting rows in that buffer, the other nodes are going to see that, okay, the buffers are now having some data, so some of the other nodes can start waking up and start doing some of their work. So the hash join, for example, can start doing some of its work. The select node can also start doing some of its work, so they will start pulling some of those rows and start executing their own code. Here the select is starting to output some rows as well. The hash join is using those rows coming from the A side to start building its hash table. So that will keep happening. And then once the hash table is built, it will also start pulling from the select side and will start joining and producing outputs. Now the limit sees that, okay, some inputs are ready, then it will wake up and start also producing some of the outputs. In this particular case, as you have seen, the limit, we have limit 2, so as soon as we get 2 results, we can just stop the query, even though there are some still intermediate results that have not been processed. We don't need them, right? So the table scan B, even though it hasn't finished scanning the table, it can stop, as well as the hash join and the selection, all that, because we produce 2 rows and that's what the query is looking for. So in this model, each node is pushing data to its parent. It's not waiting for the parent to ask it for the next row. It's just pushing the data, and the parent will start working on this data whenever it's ready. The advantage here is that multiple nodes can work in parallel, depending on how many CPUs you have, how many parallel threads you can have. You can have as many of these operations running in parallel. The disadvantage, of course, is that it's more complex. You have to do more coordination here. You have to look at the buffers, see if the buffers are empty or full, what to do when it's empty, what to do when it's full, and all that. You have to coordinate between the multiple threads, and it also makes it very complex and very difficult to debug. You can't really debug this because multiple things are happening at the same time, and each time you run the query, you might get a different sequence of things that happen. So it's not predictable. So again, there's always this trade-off between complexity and performance. So these are 2 ways of handling processing. To summarize what we've talked about today, again, today we have talked about the execution engine, which is the final step in the query engine. This is what actually produces the results. The execution engine takes an execution plan as input and starts running all the operations in this plan over the input data. There are multiple processing models which dictate how the operations are implemented. Each model will have, all the operations follow some API. We talked about the Materialization Model, which returns all the results from each node in a single call. We also talked about the Iterator Model, which is the most common one, which returns just 1 row at a time. And then we talked about the Vectorization Model, or the batch processing model, which returns a number of rows or a batch of rows for each call, and how this is a trade-off between the first 2 models. And then last but not least, we talked about the difference between pull-based and push-based processing, and how there's a trade-off between the complexity of implementation and debugging and the parallel processing and the performance of the query. I hope this was a easy video to understand. I hope it clarified how the execution engine works. Please let me know if you have any comments or questions or things that you would like me to clarify. Please hit the like button if you like this video. Please subscribe to the channel if you have not already. And with that, thank you so much for watching, and I will see you in the next video.